I'm happy if you just do this, but the back of the book will put both the sequences together, or sorry, the summations together actually, to make it all look like this. So they have the common denominators. There you go. There is our nice Maclaurin series. Okay. Now, let's go back, because I also asked us for the radius conversions. Let's go to e to the x. So e to the x has a radius convergence of infinity. So I'm not supposed to tell you guys this, but this is let's just say this is a shortcut to knowing when how to find your radius conversions. Basically, whenever your radius convergence is basically infinity, let's think about this. If I subtract a really, really big number minus a really, really big number, I still get a really, really big number, right? And notice this is getting bigger than this one, so I'm never going to be going down to 0 in this case, right? This is going to be really big minus really big. It's still going to be a huge number, like 5,000 minus 8,000, right? That difference is going to be corresponding to it. So whenever this happens, you could just kind of skip that step and just know it's going to go to infinity when it comes to that. Again, you could technically do the whole work of using, again, the ratio test, and you'll end up being like into a really, really, really big mess. And again, don't really want to do that. You eventually, if you actually do this process, you end up being you have a big old mumbo jumbo, and then within the absolute value, you have actually this happening. And again, that always goes to 0, so the radius is infinity itself. So that's the reason why. Okay, so just give you guys a hint, especially for your homework and maybe for the exam as well. Okay. All right, now let's go to the last two examples here. One of the most important ones is more examples on finding Taylor series and also radius of convergence. Okay, so we want to find the Taylor series of the function 1 over x around a equals -2. Okay. Now this does not say I want the first 4 terms, 5 terms, right? This is the general one. So what is it always going to look like no matter what? Okay. So again, can't use these because these are all Maclaurin series, right? So even though it may look like it, so for example, if we ask you find the Taylor series for, let's say, e to the x, right? We can't technically use this because it's Maclaurin, means x equals 0. Taylor series gives us a value itself. Like for example, here it is now -2. Okay, which means we have to use the definition and hopefully figure out a pattern to give ourselves out there. Okay, so let's see. So first off, according to our definition, we need to find, well, I'll just write this down. So f of x is just 1 over x, and if I plug in -2, this ends up being -1/2. Okay, taking the first derivative gives us -1 over x squared. Plug in -2, and that gives us -1/4. Taking the second derivative of this gives you +2 over x to the third. And then plug in -2 into here, and that should give you -2 over 8. Yeah. Take the third derivative. This ends up being -6 over x to the fourth. So this ends up being -6 over, I believe it's 16. Okay. And I'm going to do one more just in case, because I'm not sure if I see a pattern yet. Take the fourth derivative. That means +24 over x to the fifth. And if I plug in -2, that gives you -24 over 32. Okay. Now the question is, can we find a pattern? So in other words, what will be the nth derivative going to be? Well, the good thing is we notice it alternates sign somewhat, right? For negative, then it comes a negative again, and actually the first three negatives, well actually, oh good, they're all negatives, which is great. So nothing changes there, right? So all negative values. Okay, so therefore we're going to have negative in our process. We have some fraction. And the tops we have 1, 1, 2, 6, 24. And I told you guys kind of that pattern, right, of factorials. So if we start with zero derivative, first derivative, second derivative, third derivative, right? 6 is another way of saying 3 factorial. And if you notice, actually 24 is actually 4 factorial. So it looks like this is going to be n factorial at top. And now at the bottom, we look at the x values. Oh, what am I doing? Yeah, so look at the derivatives. Should be a 1 here. Sorry about that. 1s. And at the bottoms, we have x, x squared, x to the third, x to the fourth, x to the fifth. And again, notice, if I follow that same template we did for n's, we have zero derivative, first derivative, zero derivative, first derivative, second derivative, third derivative, fourth derivative. Notice it's this number plus 1 gives you the bottom one. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. So this looks like it's x to the n plus 1 power. And again, why are we actually doing this? Right? Because remember, the whole point is find a Taylor series for each one. And if you don't remember, a Taylor series, by definition, looks like this. It is the nth derivative at a over n factorial, right, times its power series itself. And this is what we're trying to look for, the coefficients of them respectively, or the derivatives, the general derivative of it, right, when it comes to it. Okay. So, in this process, the sequence is going to be the nth derivative, so all of this evaluated at a equals negative 2. So everywhere we see x, I'm going to plug in negative 2. So it'll be negative 1 over negative 2 to the n plus 1. Okay, so this whole thing is just this. Okay, that's it. So what we just did was just find the nth derivative of our Taylor series. Hence the reason it's just that. So now times, now we put the rest. X minus 2 ends up being plus to the n divided by n factorial. And there we go. There's our Taylor series for this function here. I know, a lot of work. All right, lastly, find the radius of conversions. So same process, do the ratio test. So I'll just, I'll just knock that off because it just goes away anyways. And again, in this case, you have to put the whole process, so you can't take each individual step. Okay. So I'll put n plus 1, n factorial. This ends up being x plus 2 times x plus 2 to the n, because it's n plus 1. And this stuff, oh, actually, great part is, notice stuff cancels before I do anything. So these actually cancel. So this is actually gone. Oh, that's great. Right, these actually cancel together. Cool, one less thing to deal with. And on the bottom, plus 1, so it's n plus 2. Like that. And times this flipped, right? So it's going to be cancel, 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 cancel. So we have this. Okay. So again, according to its ratio test, this only converges if it is less than 1. But again, we're taking the absolute value, which is nice. So what this saying is, this is the absolute value of x plus 2 over 2, so less than 1, right? The absolute value of negative 2 is just 2. Multiply this over. So the absolute value means we're going to have negative 2, or it's bounded between negative 2 and positive 2. And now we just subtract 2. So our radius converges is from negative 4 to 0. Here we go. All right, now let's do the last example here. So this one is actually a trick question. Okay. The reason why I say it's a trick question, unlike the last one for A, if I take the derivative, it just keeps going, right? It's an infinite derivative, meaning what that means is it just keeps going and going and going and going and going. Notice this, however, this derivative actually stops at a certain point. If you don't know what I'm talking about, well, you'll see what I mean in a little bit. So same thing, we want to find the Taylor series centered at a equals 2. So first off, we'll just write f of x is just this. Now if I plug in 2 into here, I should get 50. Take the first derivative. This ends up being 6x to the 5th minus 4x to the 3rd. 2 goes away. And the same thing, plug in 2. We get 160. Take the second derivative. This ends up being 30x to the 4th minus 12x squared. Plug in 2 again, and it should give you 432. Do the third derivative. This ends up being 120 minus 24x. This is 912. Plug in 2. All right. Plug in the fourth derivative. 3 times 120 is 360. X squared minus 24. This ends up being 1416. Do the fifth derivative. 2 times 360 is 720. That's gone. So this is being 1440. And now do the sixth derivative. And this is just 720. So this is what I mean. This derivative actually stops after a certain point, meaning we can actually expand the entire Taylor series, and there really is no nth derivative when it comes to it. So when it comes to this situation, so that's why it's a little trick question. This Taylor series is just according to its 50. So let me get this up so you can see here. So according to its Taylor series, it's going to be f of a, which is just 50, plus first derivative of a over 1 factorial times x minus a, or in other words, 160 over 1 factorial times x minus 2 to the first power. Next term, second derivative of a over 2 factorial times that squared. So 432 over 2 factorial times x minus 2 to the second power, and you just repeat this process until we finish everything else. And there we go. So this is this function's Taylor series. So it's unlike this one where it's an actual sequence, because this time we actually have a stopping point itself. And so, because we want a general term, we cannot find its radius of convergence. And you guys are sad that we don't have to find it.